Ladies and gentlemen, please welcome a program manager from DARPA's Information Innovation Office, Dr. Sandeep Neema.
It's pretty exciting to be here. By now, you've seen very many exciting applications of AI in various areas. Rest assured, software is not behind. We live in a world dominated by software, and DoD is no exception. Every new generation of system that we build today has an order of magnitude more software than the prior generation. The F-35 in 2012, for example, has 14 times more code than F-22. And it's not just that the amount of software in these systems is increasing, but it's also the case that the portion of critical functionality in these systems is increasingly being realized in software. So that's one trend. A parallel and not so exciting trend is that the defects or the vulnerabilities in software are also increasing at the same time. The chart on your right is from a blog post on Rapid7 that looks at CVEs across time. And as you can see in the chart, the number of CVEs that are recorded each month have almost quadrupled in the past decade or so. So on one hand, we have a large amount of software. We increasingly rely on software to implement the functionality. But at the same time, the defect or the vulnerabilities in these software systems are also increasing. Clearly not a tractable trend that we want to be in. Now, there are many explanations and hypotheses one could proffer for the state of affairs. The two we found most prominent in this context was, one, that the tools and methods that we have for software production and quality assurance are not scaling up with the amount of software that we need and build. And two, that even though we have large amount of software code base in our possession today, we don't effectively utilize that in terms of understanding the source of bugs and making sure that these bugs are not repeated and improve the software production process. So the question becomes, how can we utilize these software assets more effectively? So the one answer we came up with is if we could treat programs as data, or more appropriately, artifacts derived from programs as data. And assuming we can do that, it opens up a lot of powerful tools and techniques that are coming from the big data and machine learning community in the past decade or even less. Let me let you to think about your credit card usage as an example for a second. You don't tell the bank, let alone in a formal language, how you intend to use your credit card. And yet, the bank, based on the usage of your credit card, as well as those of people in similar demographics, can make important inferences, can infer behavioral patterns, can learn a specification of your behavior. And when suddenly an anomalous chart shows up, for example, a furniture purchase in Brazil, the bank can flag that as an anomaly. So our question was, could we not do that same thing for software? Could we, rather than looking at each program as a unique, isolated instance, which is how we do bug detection for most part today, could we look at ensembles of programs? Could we look at collectives of these programs? Could we take the properties of these programs and cluster them together? Could we learn distribution over these programs with the expectation that nominal behavior or the properties of nominal programs would cluster around some sort of a mean, whereas anomalous behavior will show up in this high variance region? So that, in a nutshell, was sort of the key insight behind this program that I'm going to talk to you about called Muse, or Mining and Understanding Software Enclaves. So in Muse, we gathered a large corpus of open source software, and we built a collection of tools and techniques inspired by big data and machine learning to achieve three capabilities critical to software development processes: code mining and semantic search, bug detection and repair, and program synthesis. Search is one of the most basic tool in every software developer's toolkit. And yet, we haven't progressed much more beyond keyword searches and indexing. So in Muse, we try to go beyond and look at higher orders of searches with semantic labels, semantic similarity, and those kinds of things. The state of art in bug detection repair, for most part, is static and dynamic analysis tools that operate on each program one at a time. In Muse, we try to use learning-based approaches and ensemble-based approaches for anomaly detection. Similarly, in program synthesis, the state of art is code generation using higher order, higher level domain-specific or domain-specific modeling languages, which still require a significant specification effort. In Muse, we try to build approaches that require very little specification, even partial or incomplete specification, and generate significant program artifacts from that specification. OK, so in the next few charts, what I intend to do is give you a couple representative examples from each of these capability areas. But I'm going to tell it as a story from the perspective of a software developer. OK? So let's imagine that we have a software developer who joins an organization. Now, this organization has large code base, and as usual, not enough documentation. So the first thing that this developer has to do is to understand this code base, make sense of it. Obviously, he's wondering, isn't there a way to do this without requiring me to pore through the entire code base line by line? And since this is the AI Colloquium, I get to say this. There is an AI for that. OK, so in this application, the system, which we are referring to as mining engine, takes as input arbitrary source code and provides some semantic information about this source code. So this example is a Java program, uses arrays in Java, uses generics. And the summary here is that the program tests the array clone method and prints the output class. So pretty accurate description of this code. Now, of course, we do get some funny descriptions also, which have similar to the child holding a baseball bat kinds of examples. But for most part, this works reasonably well. So let's look at how does this work. Well, this is a very classical convolutional neural network kind of approach. And the network in this case has been trained over a collection of Stack Overflow posts. Stack Overflow, for those who do not know, is a portal for developers, where a typical interaction is in the form of a developer asking a question about how a particular capability is achieved in software, and some other developer responding with a code snippet, as well as some description of how this code works, as well as some semantic labels for that code. So that provides us a rich labeled data set that we can train this network over and use that to now classify and read these kind of arbitrary inputs and generate code in tags. This approach is built on work by 26 Labs and works pretty well for most cases. But there are situations where you need more than just semantic description and labels. There are situations when you want to find other similar programs which may be more efficient implementation of something that you're doing, or maybe more readable implementation of something that you need. So for that, there's a complementary approach. And in this case, the input, again, is in the form of C or C++ functions. And the mining engine, in this case, finds and returns a collection of most similar functions. How does this work? Well, this is based on clustering techniques. And the system, again, is trained over a collection of C, C++ programs. These functions or programs are mapped into a feature space and clustered in that feature space. The typical features here are the classical things that you'll see in programming artifacts, like control flow graphs, like type signatures, like the instruction frequencies, and so on. And when you present an arbitrary input to the system, it basically maps the program into the feature space, and then looks at things which are closest in terms of distance in the feature space. And then it gives you these kind of similar functions. A prominent use case for something like this is when you're doing malware binary analysis. And typically, binary analysis, you can use decompilers that will give you some sort of an output, but that's very difficult to understand. So again, you can use a system like this to give you more interpretable representations of that function. OK, so let's think back about our software developer. He's joined this organization. Now he's able to parse the code. He has all the necessary tools to make sense of the code base. Of course, the next thing he's going to get assigned to is go and find and fix bugs in the repository, right? Well, again, we have an AI for that. So this system takes buggy programs like this and then generates a patch program for a narrow class of bugs. So the specific example here is an array out of bound type of bug. The array on the top that you see highlighted in red is too small for the code that's operating on it. And when this code is executed, it will result in an exception. So when you feed this input to the mining engine, it can fix this by increasing the size of the array. How does this work? It's also another neural network application, but in this case, it's doing sequence-to-sequence transformations. Similar idea is what you'll see in English grammar correction. It uses an autoencoder with long short-term memory, and the system is trained over a collection of buggy and patched code. And the output it produces is a fixed software. This comes from a work at Draper Labs. It's effective in sort of narrow classes of bugs, and especially when the bugs are such that the context of the bug and the output is close in terms of the function distance, but suffers from the similar limitations that you'll see in neural network. For example, it will require a huge amount of training data set, label training data set, still has pretty high false positive rates. Another approach, an alternate to this, that's much more robust and mitigates some of these problems, complements machine learning kind of techniques with classical computer science-based approaches. And that's here. So the input and output for this system is similar. You present a buggy code, and it produced a fixed code. The specific bug scenario here is from a PHP interpreter, which is a very large body of code, more than 1 million lines of software. And the specific bug here is that the API call, the initialized call, is not conditioned sufficiently to protect that call when the string is null. The system takes this kind of an input and generates, modifies this code, and extends the condition to check for the null string. OK, so how does this work? Now, this one, as I said, it takes classical computer science-like approach. It forms a search space around the buggy region of the program, looks at potential modification within that region of the program, and constructs a pretty large search space. For each modification in that search space, it constructs a patch, compiles that patch, and tests it, and then finds if the patch is correct or not. Now, that would work, except that the search space is so large that by the time you get to finding the actual correct patch, you run out of your computational resources. So they address that limitation by complementing with machine learning-based approaches. Now, in this case, the machine learning approach comes in the form of training a predictor that can take the bug, the context of the bug, and predict the likelihood of this particular patch being the correct patch in this context. And again, it's trained with a set of buggy and patch software, human-generated patches. So now once you have these kind of likelihood estimates, you, rather than exploring the whole search space, you rank these candidate patches based on their likelihood, and you apply only the top few. And the results are pretty good in the sense that for most of the cases, 90% of the cases that they've tried this out with, the correct patch lands up in the top 4 or less. This comes from a group at MIT, and the system that's referred here is called Prophet. OK, so let me talk back about our software developer. So he has demonstrated himself. He has proven his capabilities by understanding the code base. He knows how to fix code. So obviously, the next thing he gets assigned to is to write software on his own. OK. So here again, we have an AI to help him with that. And in this case, the AI works by generating programs from very little or very limited specifications. So the specification in this particular example is pretty small. It just has a type signature for the type of function that you want to implement. And here what you want to do is you want to implement a function that reads lines from a file. So the mining engine in this case takes a very little specification like that and generates a pretty complete code which calls the right API calls, has all the right variable assignments, has the right looping structure, and so on, a correct and compilable code. How is this working? This is using ideas from generative modeling techniques, specifically variational autoencoders. And what that autoencoder is doing is essentially learning a probabilistic relation between behavioral and structural features of the programs. Behavioral features are things like call sequences, type signatures, even natural language comments. Whereas structural features are basically implementations, but abstracted away from details. So now when you present an arbitrary input to this system, it will extract the behavioral features from that program, and then use that behavioral feature to to estimate the posterior distribution from the space of all possible sketches as which one is the most likely structural feature that corresponds to these set of behavioral features. And then once you can sort of narrow down the set of sketches that correspond to that behavioral feature, then the rest of the system can take those sketches and concretize that into an implementation. This is a system called Bayou and has been implemented by Rice University. Now, the system works for small program generation, and there are efforts afoot to sort of extend the scope of it and building much larger programs. But when you talk about more complex functionality and functionality that's critical to your system, it's not sufficient to just produce an implementation, but you want also some evidence, a proof that this implementation is correct and implements your specification correctly, right? So let me disappoint you and say that we don't have an AI for that. But we have something that gets quite close. So this system has two parts. One is sort of the classical corpus-based approach, which helps you find good implementation, so uses the semantic similarity kinds of ideas and helps you find implementation. But it gives you not only an implementation, along with the implementation, it also gives you a logic-based extraction of that implementation. And when you have a specification of what you want that functionality to be, then the system allows you to construct these rewriting transformations that takes the high-level specification and maps it down into the low-level implementation, low-level specification. Now, this is a semi-automated approach in the sense that the transformations, there is a library of transformations that you can pick from, but the sequencing of this transformation is something that you have to come up on your own. So there is some manual effort required in that process. But once you can come up with the sequencing of transformations, these logically writing transformations, then you know by construction that the implementation is a correct implementation of that specification. This comes from a work by Kestrel. OK, so to wrap up, what I did was I gave you some examples of applications of AI in various areas of software development, critical capabilities. The things that I showed you are generally research prototypes, but we've had good transition pathway by working with GitHub. And several of the techniques that I mentioned here are getting transitioned into GitHub to make it accessible to a larger community of developers. The artifacts that we collected in this program, the software corpus, the tools that we developed, the publications, all of these are available through the site, themuseportal.net. Now, let me leave you behind with the most important takeaway. The program was started in 2014, and the community of researchers that we have inspired since then has truly ushered in this era of big code. And I expect that developments that's coming through this program and beyond will fundamentally transform how we build and maintain software in the future. Thank you. So the question here is that the examples that you presented on code mining and semantic search, bug detection and repair, and program synthesis were conducted at small scales. What is limiting these approaches from working at large scales? So let me qualify my statement a bit by telling that it's not that all of these are at small scale. The bug repair example that I showed you, specifically the one that was combining machine learning and computer science-based approach, was actually applied to a very large code base, right? That's a PHP interpreter. It's a pretty sizable case. Now, some of the approaches which are based purely on neural network, they do currently work at small scale. And there are multiple sort of factors why that is the case. Some of it is limitations of the infrastructure itself. So just for us to extract all the semantic artifacts from these programs, build it into a database, process that, that's quite a huge artifact set. And limitations here are coming from just the infrastructure that we use underneath these things. A more important limitation that I believe, though, is coming from currently we are taking all of these sort of the neural network-based approaches, which are primarily built for data sets that come from Euclidean spaces normally. And we are trying to coarse this software design data. These are typically non-Euclidean artifacts, right? And try to coarse it into these kind of representations and approaches. And so there is a representation mismatch in this case, which makes it difficult to scale it. Now, there are new techniques that are coming in this direction, particularly with respect to graph neural networks and so on, which offers a path forward to extend these approaches and make them more scalable. So the second question here that says, have you conducted any studies or comparisons to show how much reduction in software development time you can gain using these approaches? So in the program, we haven't done a systematic study that does these kind of comparisons. But there are some areas where it's sort of reasonable to do the comparison. For example, in program synthesis, one could just look at the size of the program artifacts that we produce and how much time it will take to generate these artifacts by hand. So that gives you some sort of a direct basis to do the comparison. In bug detection and repair, it's difficult to do the comparison because the time to fix the bugs sort of depends on the complexity of the bugs. So there's not really a direct comparison. But we haven't conducted any systematic studies yet in that respect. There's another question here that's, beside your performers in GitHub, are there DoD organizations that are leveraging these tools to search, synthesize, and repair software? So not directly, but we have had interaction with several of DoD researchers in the course of the program who are looking at taking techniques that are coming from this program and applying in that context. We've had interactions with folks at JIDO. We've had meetings with folks at CERDEC who are looking to apply these techniques. So that's all the questions that I had. Thank you.